2 arrays and structures. 2.1 The array as an abstract data type. 2.2 Structures and union structures unions. 2.2.1 2.2.56 Internal implementation of structures. 49 2.2.3 53 57 6 Contents. 2.3 2.4 Introduction. 66 2.5 2.6 2.7 2.8 57 59 66 2.2.4 Self-referential structures. The polynomial abstract data type. The sparse matrix abstract data type. 2.4.1 2.4.2 Transposing a matrix. 2.4.3 Matrix multiplication. The representation of multidimensional arrays. The string abstract data type. 82.6.1 80 Introduction. 2.6.2 Pattern matching. References and selected readings. Additional exercises. 92-84 Chapter 3. Chapter 2 Arrays and Structures. 2.1 The array as an abstract data type. We begin our discussion by considering an array as an ADT. This is not the usual perspective. Essence. Many programmers view an array only as a consecutive set of memory locations. This is unfortunate because it clearly shows an emphasis on implementation issues. Thus, although an array is usually implemented as a consecutive set of memory locations, this is not always the case. Intuitively, an array is a set of pairs, index, value, such that each index that is defined has a value associated with it. In mathematical terms, we call this a correspondence or a mapping. However, when considering an ADT, we are more concerned with the operations that can be performed on an array. Aside from creating a new array, most languages provide only 2 standard operations for arrays, one that retrieves a value and a second that stores a value. Structure 2.1 shows a definition of the array ADT. The cre_j_list function produces a new, empty array of the appropriate size. All of the items are initially undefined. Retrieve accepts an array and an index. It returns the value associated with the index if the index is valid, or an error if the index is invalid. Store accepts an array, an index, and an item, and returns the original array augmented with the new index, value, pair. The advantage of this ADT definition is that it clearly points out the fact that the array is a more general structure than a consecutive set of memory locations. 49. 50 Arrays and Structures. Array create. 7 List. Structure. Array is objects, a set of pairs, dex, value, where for each value of index there is a value from the set item. Index is a finite ordered set of 1 or more dimensions, for example, a 0, and 1 for 1 dimension, 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2, for 2 dimensions, etc. Functions for all a G array, ig index, x G item, j, size G integer. Return an array of j dimensions where list is a y-tuple whose zth element is the size of the zth dimension. Items are undefined. If zg index, return the item associated with index value z in array a, else return error in index. Return an array that is identical to array a except the new pair a z. X has been inserted, else return error. Item retrieve a / array store a z x. End array. Structure 2.1 Abstract data type array. Now, let's examine arrays in C. We restrict ourselves initially to one-dimensional arrays. A one-dimensional array in C is declared implicitly by appending brackets to the name of a variable. For example, int list 5 *list 5. declares two arrays each containing 5 elements. The first array defines 5 integers, while the second defines 5 pointers to integers. In C, all arrays start at index 0, so /C5, 0, ZZ caret RFL, /Z5R, 2, /Z5Z, 3, and /Z_F4 are the names of the 5 array elements, each of which contains an integer value. Similarly, plist Q, plist, plisl, plist3, and plist4 are the names of 5 array elements, each of which contains a pointer to an integer. We now consider the implementation of one-dimensional arrays. When TheCompiler encounters an array declaration, such as the one used above to create list, it allocates 5 consecutive memory locations. Each memory location is large enough to hold a single integer. The address of the first element /Z5Z0 is called the base address. If the size of an integer on your machine is denoted by sizeofind, then we get the following memory addresses for the 5 elements of list dash. The array as an abstract data type 51 variable to 0 z caret dl /c5 2 /c5 3 /wr4 memory address base address equals a plus size of int a plus 2 size of int a plus 3 foot size of int a plus 4 size of mt. In fact, when we write list I in a C program, C interprets it as a pointer to an integer whose address is the one in the table above. Observe that there is a difference between a declaration such as int lisl and int list2 5. The variables list and list2 are both pointers to an int, but in the second case 5 memory locations for holding integers have been reserved. List2 is a pointer to /C5R20 and list2 plus I is a pointer to ust2 I. Notice that in C, we do not multiply the offset I with the size of the type to get to the appropriate element of the array. Thus, regardless of the type of the array list2, it is always the case that to 2 plus / equals and list2 IO. So, Stern list2 plus Z equals list2 I. It is useful to consider the way C treats an array when it is a parameter to a function. All parameters of a C function must be declared within the function. However, the range of a one-dimensional array is defined only in the main program since new storage for an array is not allocated within a function. If the size of a one-dimensional array is needed, it must be either passed into the function as an argument or accessed as a global variable. Consider program 2.1. When sum is invoked, input equals and input 0 is copied into a temporary location and associated with the formal parameter list. When /C5R a ZJ occurs on the right-hand side of the equals sign, a dereference takes place and the value pointed at by list plus C is returned. If list I appears on the left-hand side of the equals sign, then the value produced on the right-hand side is stored in the location list for Z. It is useful to consider the way C treats an array when it is a parameter to a function. All parameters of a C function must be declared within the function. However, the range of a one-dimensional array is defined only in the main program since new storage for an array is not allocated within a function. If the size of a one-dimensional array is needed, it must be either passed into the function as an argument or accessed as a global variable. Consider program 2.1. When sum is invoked, input equals and input 0 is copied into a temporary location and associated with the formal parameter list. When /C5R a ZJ occurs on the right-hand side of the equals sign, a dereference takes place and the value pointed at by list plus C is returned. If list I appears on the left-hand side of the equals sign, then the value produced on the right-hand side is stored in the location list for Z. Thus in C, array parameters have their values altered, despite the fact that the parameter passing is done using call by value. Example 2.1 One-dimensional array addressing. Assume that we have the following declaration, int 1, 0, 1, 2, 3, 4. We would like to write a function that prints out both the address of this element of this array and the value found at this address. To do this, Print \o program 2.2 uses pointer arithmetic. The function is invoked as print and 1, 5. As you can see, 52 arrays and structures hashtag define max size 100 float sum, float, int, float input, max size, answer, int I, void main void 0, I max size, I++, 4, I input, i.e. answer sum, input, max size. Printf, the sum is %f\n answer, 1, a float sum, float list, int n is 0, 0, I int I, float temp sum equals 0, for I equals n, temp sum plus equals list, I, return temp sum, a program 2.1, example array program. From the printf statement, the address of the ith element is simply ptr plus I. To obtain the value of the /th element, we use the dereferencing operator, star. Thus, $ptr plus / indicates that we want the contents of the ptr4 I position rather than the address. Void printle, int / print out a *ptr int rows. One-dimensional array using a pointer in I. Printf, address contents \n, for I equals 0, rows I printf, to printf, \n, */q, %8u %5d \n, I++, ptr plus I, ptr plus I, asterisk. Program 2.2, one-dimensional array accessed by address figure 2.1 shows the results we obtained when we ran print1. Notice that the structures and unions 53 address 1228, 1230, 1232, 1234 contents 0, 1234 figure 2.1, one-dimensional array addressing. Addresses increase by 2. This is what we would expect on an Intel 386 machine. 2.2 structures and unions 2.2.1 structures. Arrays are collections of data of the same type. In C, there is an alternate way of grouping data that permits the data to vary in type. This mechanism is called the struct, short for structure. A structure, called a record in many other programming languages, is a collection of data items where each item is identified as to its type and name. For example, struct char name 10 int age. Float salary. A person creates a variable whose name is person and that has 3 fields, a name that is a character array and integer value representing the age of the person. A float value representing the salary of the individual. We may assign values to these fields as below. Notice the use of the as the structure member operator. We use this operator to select a particular member of the structure. 54 arrays and structures 10, strcpy, person, name, James, person, age person, salary equals 35,000. We can create our own structure data types by using the typedef statement as below. Typedef struct human being, char name, 10.3, int age, float salary. Or typedef struct char name, 10, int age, float salary, human being. This says that human being is the name of the type defined by the structure definition, and we may follow this definition with declarations of variables such as human being personal, person2. We might have a program segment that says, if strcmp, personnel to name, person2 to name, printf, the two people do not have the same name xn, else printf, the two people have the same name \n. It would be nice if we could write if personal equals person2 and have the entire structure checked for equality. Or if we could write personal equals person2 and have that mean that the value of every field of the structure of person is assigned as the value of the corresponding field of person1. ANSI C permits structure assignment, but most earlier versions of C do not. For older versions of C, we are forced to write the more detailed form, strcpy, personnel to name, person2 to name. Personal.age equals person2 to age. Person salary equals person2 salary. While structures cannot be directly checked for equality or inequality, we can write a function, program 2.3, to do this. We assume that true and false are defined as To find false 0, to find true 1, a typical function call might be. Structures and unions 55 and humans equal, human being personal, human being person 2, / being otherwise return false return true if personal and if strcmp, personnel name, person 2 name, return false. If personal age equals person 2 age, return false. If personal salary 1 equals person 2 salary, return false, return true. Person 2 are the same human */ program 2.3 function to check equality of structures. If humans equal personal person 2, printf, the two human beings are the same \n, else printf, the two human beings are not the same \n. We can also embed a structure within a structure. For example, associated with our human being structure, we may wish to include the date of his or her birth. We can do this by writing typedef struct int month, int day, int year, a date, typedef struct human being char name, 10 int age, float salary, date dob. A person born on February 11th, 1944, would have the values for the date struct set as 56 arrays and structures personal, dob, month equals 2, personal, dob, date equals 11, personal, dob, year equals 1944, 2.2.2 unions. Continuing with our human being example, it would be nice if we could distinguish between males and females. In the case of males, we might ask whether they have a beard or not. In the case of females, we might wish to know the number of children they have born. This gives rise to another feature of C called a union. A union declaration is similar to a structure, but the fields of a union must share their memory space. This means that only one field of the union is active at any given time. For example, to add different fields for males and females, we would change our definition of human being to typedef struct sex type enum tag field female, male sex, union and children. Int beard, u. Typedef struct human being, char name, 10 int age, float salary, date dob, sex type sex info. A human being personal, person 2, we could assign values to person and person 2 as personal to sex info, sex equals male, personal, sex info, beard equals false, and person 2, sex info, sex equals female, person 2, sex info, children 4. Notice that we first place a value in the tag field. This allows us to determine which field in the union is active. We then place a value in the appropriate field of the union. For example, if the value of sexinfo.sex was male, we would enter a true or a false in. Structures and unions 57. The sexinfo beard field. Similarly, if the person was a female, we would enter an integer value in the sexinfo u.children field. C does not check to make sure that we use the appropriate field. For instance, we could place a value of female in the sexinfo.sex field and then proceed to place a value of true in the sexinfo beard field. Although we know that this is not appropriate, C does not check to make sure that we have used the correct fields of a union. 2.2.3 Internal implementation of structures. In most cases, you need not be concerned with exactly how the C compiler will store the fields of a structure in memory. Generally, if you have a structure definition such as struct int I j, float a b, or struct int I int j, float a, float b, these values will be stored in the same way using increasing address locations in the order specified in the structure definition. However, it is important to realize that holes or padding may actually occur within a structure to permit two consecutive components to be properly aligned within memory. The size of an object of a struct or union type is the amount of storage necessary to represent the largest component. Including any padding that may be required, structures must begin and end on the same type of
Including any padding that may be required. Structures must begin and end on the same
Including any padding that may be required, Structures must begin and end on the same type of memory boundary, for example, an even byte boundary or an address that is a multiple of 4, 8, or 16. 2.2.4. Self-referential structures. A self-referential structure is one in which one or more of its components is a pointer to itself. Self-referential structures usually require dynamic storage management routines, malloc and free, to explicitly obtain and release memory. Consider as an example link. Typedef struct list char data list. Each instance of the structure list will have two components, data and link. Data is a single character, while link is a pointer to a list structure. The value of link is either the address in memory of an instance of list or the null pointer. Consider these statements, which create three structures and assign values to their respective fields. 58 arrays and structures list item/item, data item 2, data item 3, data item link item 2, C, item 2, link item 3 to link null. Structures item 1, item 2, and Z7M3 each contain the data item A, B, and C, respectively, and the null pointer. We can attach these structures together by replacing the null link field in item 2 with one that points to item 3, and by replacing the null link field in item 1 with one that points to item 2. And item 2, link equals, and item 3. We will see more of this linking in Chapter 4. Exercises 1, 2, 3. Develop a structure to represent the planets in the solar system. Each planet has fields for the planet's name, its distance from the sun in miles, and the number of moons it has. Place items in each the fields for the planets, Earth and Venus. Modify the human being structure so that we can include different information based on marital status. Marital status should be an enumerated type with fields: single, married, widowed, divorced. Use a union to include different information based on marital status as follows. Single. No information needed. Married. Include a marriage date field. A widowed. Include marriage date and death of spouse date fields. Divorced. Include divorce date and number of divorces fields. Assign values to the fields for some person of type human being. Develop a structure to represent each of the following geometric objects: rectangle, triangle, circle. Structures and unions 59 2.3 The polynomial abstract data type. Arrays are not only data structures in their own right, we can also use them to implement other abstract data types. For instance, let us consider one of the simplest and most commonly found data structures, the ordered or linear list. We can find many examples of this data structure, including days of the week: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, diamond suit values in a deck of cards: ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. Floors of a building: basement, lobby, mezzanine, first, second. Years the United States fought in World War II: 1941, 1942, 1943, 1944, 1945. Years Switzerland fought in World War II. Notice that the years Switzerland fought in World War II is different because it contains no items. It is an example of an empty list, which we denote as. The other lists all contain items that are written in the form item Q, item J, item I. We can perform many operations on lists, including diamond suit finding the length, n of a list. Diamond suit reading the items in a list from left to right, or right to left. Retrieving the /th item from a list, 0, I less than n. Replacing the item in the /th position of a list, 0, /. Inserting a new item in the /th position of a list, 0, I less than n. The items previously numbered /I 4 to 1, n, 1 become items numbered /4-1, /4-2, n. Deleting an item from the /th position of a list, 0, /n. The items numbered /4 to 1, L become items numbered /4-1, N2.
N.
Rather than state the formal specification of the ADT list, we want to explore briefly its implementation. Perhaps the most common implementation is to represent an ordered list as an array, where we associate the list element, items, with the array index I. We call this a sequential mapping because, assuming the standard implementation of an array, we are storing items plus / into consecutive slots I and I plus 1 of the array. Sequential mapping works well for most of the operations listed above. Thus, we can retrieve an item, replace an item, or find the length of a list in constant time. We also can read the items in the list from either direction by simply changing subscripts in a controlled way. Only insertion and deletion pose problems since the sequential allocation forces us to move items so that the sequential mapping is preserved. It is precisely this overhead that leads us to consider non-sequential mappings of ordered lists in Chapter 4. 60 Arrays and Structures. Let us jump right into a problem requiring ordered lists, which we will solve by using one-dimensional arrays. This problem has become the classical example for motivating the use of list processing techniques, which we will see in later chapters. Therefore, it makes sense to look at the problem and see why arrays offer only a partially adequate solution. The problem calls for building a set of functions that allow for the manipulation of symbolic polynomials. Viewed from a mathematical perspective, a polynomial is a sum of terms, where each term has a form x caret, where x is the variable, I is the coefficient, and e is the exponent. Two example polynomials are ax equals plus 4 and bx equals plus lox caret plus 3x caret plus 1. The largest or leading exponent of a polynomial is called its degree. Coefficients that are 0 are not displayed. The term with exponent equal to 0 does not show the variable since x raised to a power of 0 is 1. There are standard mathematical definitions for the sum and product of polynomials. Assume that we have two polynomials, ax equals and bx equals j caret h slash x, then ax plus bx equals caret ai plus by x ax bx equals. Similarly, we can define subtraction and division on polynomials, as well as many other operations. We begin with an ADT definition of a polynomial. The particular operations, in part, are a reflection of what will be needed in our subsequent programs to manipulate polynomials. The definition is contained in Structure 2.2. We are now ready to make some representation decisions. A very reasonable first decision requires unique exponents arranged in decreasing order. This requirement considerably simplifies many of the operations. Using our specification and this stipulation, we can write a version of add that is closer to a C function program 2.4, but is still representation independent. This algorithm works by comparing terms from the two polynomials until one or both of the polynomials becomes empty. The switch statement performs the comparisons and adds the proper term to the new polynomial, d. If one of the polynomials becomes empty, we copy the remaining terms from the non-empty polynomial into d. With these insights, suppose we now consider the representation question more carefully. One way to represent polynomials in C is to use typedef to create the type polynomial as below. #define typedef / max 1 * max degree 101 degree of polynomial plus struct in degree. The polynomial abstract data type 61FL xn plus structure polynomial is object / x equals a caret x caret x caret, a set of ordered pairs of ej, ai, or flyin. Coefficients and c, in exponents, e caret are integers equals 0 functions. For all poly / poly 2e polynomial, coefficients, expon exponents polynomial 0, coefficient coef poly expon. Exponent lead exp, p/y, polynomial attach, p/y, coef, expon, polynomial remove, p, zy, expon, polynomial single multiple, p less than 9/y, coef, expon, polynomial add, p, zil, poly 2, polynomial multiple, Pazil, poly 2. Return the polynomial, p% equals 0 if, poly. Return false else return true if expon e poly. Return its coefficient else return 0 return the largest exponent in p/y. If expon e poly, return error else return the polynomial poly with the term coef, expond inserted if expon e poly. Return the polynomial poly with the term whose exponent is expon deleted. Else return error return the polynomial poly, coef x happy face, p happy face, return the polynomial poly I plus poly 2 return the polynomial poly / poly 2 boolean, s7 to qxq poly e end polynomial. Structure 2.2 Abstract data type polynomial float coef, max degree, polynomial. And now if FL is of type polynomial and n max degree, the polynomial a x equals x I equals 0 would be represented as a dot degree equals n. 62 arrays and structures D0, a plus b, where a, b, and d are polynomials / d while is 0, a, and is 0, b. Do a switch compare, lead exp, a, lead exp b, a case -1 d. Attach, d, coef, b, lead exp b, lead exp b, b equals remove, b, lead exp b, break, 0, 0, coef, lead exp, a, case sum lead exp b, if sum. Attach, d, sum, lead exp, a, equals remove, a, lead exp, a. B equals remove, b, lead exp b, break, case 1, d equals attach, d, coef, a, lead exp, a, lead exp, a remove, a, lead exp, a, coef, b, plus, insert any remaining terms of a or b into d. Program 2.4. Initial version of pad function a. Coef 10 z less than n equals. In this representation, we store the coefficients in order of decreasing exponents, provided a term with exponent ni exists, ni that a. Coef z is the coefficient of x such. Otherwise, a. Coef z equals 0. Although this representation leads to very simple algorithms for most of the operations, it wastes a lot of space. For instance, if a. Degree max degree, the double less than should be read as is much less than, then we will not need most of the positions in a coef max degree. The same argument applies if the polynomial is sparse, that is, the number of terms with non-zero coefficient is small relative to the degree of the polynomial. To preserve space, we devise an alternative representation that uses only one global array, terms, to store all our polynomials. The C declarations needed are max terms 100 * size of terms array * /typedef struct float coef in expon. The polynomial abstract data type 63 polynomial terms max terms in avail 0. Consider the two polynomials a x equals 2x happy face. Figure 2.2 shows how these polynomials are stored in the array terms. The index of the first term of a and b is given by starta and start, respectively, while finisha and finish give the index of the last term of a and b. The index of the next free location in the array is given by avail. For our example, starta equals 0, finisha equals 1, start equals 2, finish equals 5, and avail equals 6. Plus 1 and b, x, equals plus 10% plus 3x plus 1. Starta 4. Finisha for start finish for avail for 1 1 1 10 1 3 exp 1000 40 3200 1 1 3 4 5 6 Figure 2.2 Array representation of two polynomials. This representation does not impose any limit on the number of polynomials that we can place in terms. The only stipulation is that the total number of non-zero terms must be no more than max terms. It is worth pointing out the difference between our specification and our representation. Our specification used poly to refer to a polynomial, and our representation translated poly into a start-finish pair. Therefore, to use AX, we must pass in starta and finisha. Any polynomial A that has n non-zero terms has starta and finisha such that finisha equals starta plus n1. Before proceeding, we should evaluate our current representation. Is it any better than the representation that uses an array of coefficients for each polynomial? It certainly solves the problem of many zero terms since AX equals 2x4. One uses only 6 units of storage. 1 for starta, 1 for finisha, 2 for the coefficients, and 2 for the exponents. However, when all the terms are non-zero, the current representation requires about twice as much space as the first one. Unless we know beforehand that each of our polynomials has few zero terms, our current representation is probably better. We would now like to write a C function that adds two polynomials a and b, represented as above, to obtain d equals a4, b. To produce d, x, pad, program 2.5, adds a, x, and b, x, term by term. Starting at position avail, attach, program 2.6, places the term s of d into the array terms. If there is not enough space in terms to accommodate d, an error message is printed to the standard error device and we exit the program with 64 arrays and structures an error condition. Int finish, asterisk finished, asterisk int void pad, int starta, int finisha, int start, int / asterisk slash add x and b, x, to obtain d, x, float coefficient. Start equals avail, while starta equals finisha and start equals finish. Switch, compare, terms starta, expon, terms start that expon. Expon -1 / b expon case 0 / asterisk. Attach, terms start.coef, terms start, expon, start ++ break, equal exponents coefficient terms starta.coef plus terms start.coef, if coefficient, attach, coefficient, terms starta.expon. Starta ++ start ++ break, case 1 / asterisk a greater than b expon attach, terms starta.coef, terms starta.expon, starta ++ 1 caret add in remaining terms of a, x, for starta equals finisha, starta ++. Attach, terms starta.coef, terms starta.expon, add in remaining terms of b, x, for start equals finish, start ++, attach, terms start, coef, terms start, expon, finished equals avail, 1, asterisk / asterisk caret /. Program 2.5, function to add two polynomials. Analysis of pad dash. Since the number of non-zero terms in A and in B are the most important factors in the time complexity, we will carry out the analysis using them. Therefore, let Tn and n be the number of non-zero terms in A and B, respectively. If Tn 0 and n greater than 0, the while loop is entered. Each iteration of the loop requires 0, 1 time. At each. The polynomial abstract data type 65 void attach, float coefficient, in exponent, a / asterisk add a new term to the polynomial * if avail equals max terms. Print stare, too many terms in the polynomial \n, exit 1. Terms avail 1.coef equals coefficient, terms avail ++, expon equals exponent, a program 2.6. Function to add a new term. Iteration, we increment the value of starta or starp or both. Since the iteration terminates when either starta or starp exceeds finisha or finish, respectively, the number of iterations is bounded by m plus n1. This worst case occurs when n x equals 2x c equals o2i. N and s, x, equals xi equals q2 z plus 1. The time for the remaining two loops is bounded by O, n plus m, because we cannot iterate the first loop more than m times and the second more than n times. So, the asymptotic computing time of this algorithm is O, a2 plus m. Before proceeding, let us briefly consider a few of the problems with the current representation. We have seen that as we create polynomials, we increment a veil until it equals max terms. When this occurs, must we quit? Given the current representation, we must unless there are some polynomials that we no longer need. We could write a compaction function that would remove the unnecessary polynomials and create a large, continuous available space at one end of the array. However, this requires data movement, which takes time. In addition, we also must change the start and end indices for each polynomial moved. That is, we change the values of starty and finisher for all polynomials moved. In Chapter 3, we let you experiment with some simple compacting routines. Exercises 1. Write functions readPoly and printPoly that allow the user to create and print polynomials. 66 arrays and structures 2 minus 2xx caret plus x, I plus asterisk plus x, h I x caret plus I 2. Write a function, pmult, that multiplies two polynomials. Figure out the computing time of your function. 3. Write a function, pval, that evaluates a polynomial at some value, xq. Try to minimize the number of operations. 4. Let ax equals I plus x caret I x and b x equals x caret x caret t x asterisk. For these polynomials, determine the exact number of times each statement of pad is executed. 5. The declarations that follow give us a third representation of the polynomial ADT. Terms /0. Expand gives the number of non-zero terms in the /th polynomial. These terms are stored, in descending order of exponents, in positions /emw, l, terms. Create the functions readPoly, printPoly, pad, and pmult for this representation. Is this representation better or worse than the representation used in the text? You may add declarations as necessary. To find max terms 101 to find max polys 15 ***. Maximum number of terms +1 * maximum number of polynomials * typedef struct float coef in expon. A polynomial terms max polys, max terms. 2. For the sparse matrix abstract data type. 2.4.1 Introduction. We now turn our attention to a mathematical object that is used to solve many problems in the natural sciences, the matrix. As computer scientists, our interest centers not only on the specification of an appropriate ADT, but also on finding representations that let us efficiently perform the operations described in the specification. In mathematics, a matrix contains m rows and n columns of elements as illustrated in Figure 2.3. In this figure, the elements are numbers. The first matrix has 5 rows and 3 columns. The second has 6 rows and 6 columns. In general, we write mxn read m by n to designate a matrix with m rows and n columns. The total number of elements in such a matrix is mn. If m equals n, the matrix is square. The standard representation of a matrix in computer science is a two-dimensional array defined as max rows, max calls. With this representation, we can locate quickly any element by writing a z, y, where I is the row index and j is the column index. However, there are some problems with this standard representation. 4. The sparse matrix abstract data type 67 row 0 row 1 row 2 row 3 row 4 call 0 call 1 call 2 minus 27,109 12 48 82 minus 2 minus 64 27 11 47 A row 0 row 1 row 2 row 3 row 4 row 5 call 0 call 1 15 11 91 call 2 call 3 call 4 call 5 22 minus 6 28 B minus 15 6 3 8 4 9 0 0 0 0 0 0 3 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 Figure 2.3. 2 matrices. Instance, if you look at Figure 2.3b, you notice that it contains many 0 entries. We call this a sparse matrix. Although it is difficult to determine exactly whether a matrix is sparse or not, intuitively we can recognize a sparse matrix when we see one. In Figure 2.3b, only 8 of 36 elements are non-zero, and that certainly is sparse. Since a sparse matrix wastes space, we must consider alternate forms of representation. The standard two-dimensional array implementation simply does not work when the matrices are large, since most compilers impose limits on array sizes. For example, consider the space requirements necessary to store a 1000 by 1000 matrix. If this matrix contains mostly zero entries, we have wasted a tremendous amount of space. Therefore, our representation of sparse matrices should store only non-zero elements. Before developing a particular representation, we first must consider the operations that we want to perform on these matrices. A minimal set of operations includes matrix creation, addition, multiplication, and transpose. Structure 2.3 contains our specification of the matrix ADT. Before implementing any of these operations, we must establish the representation of the sparse matrix. By examining Figure 2.3, we know that we can characterize uniquely any element within a matrix by using the triple row call value. This means that we can use an array of triples to represent a sparse matrix. Since we want our transpose operation to work efficiently, we should organize the triples so that the row indices are in ascending order. We can go one step further by also requiring that all the triples for any row be stored so that the column indices are in ascending order. In addition, to ensure that the operations terminate, we must know the number of rows and columns and the number of non-zero elements in the matrix. Putting all this information together suggests that we implement the create operation as below. 68 Arrays and structures. Structure sparse matrix is objects, a set of triples, a row, column, value, where row and column are integers and form a unique combination, and value comes from the set item. Functions. For all A, B sparse matrix, xe item, I, j, max call, max row G index sparse matrix create, max row, max call, colon equals. Return a sparse matrix that can hold up to max items equals max row x max call and whose maximum row size is max row and whose maximum column size is max call. Sparse matrix transpose A, colon equals. Return the matrix produced by interchanging the row and column value of every triple. Sparse matrix add FL, B, colon equals if the dimensions of A and B are the same. Return the matrix produced by adding corresponding items, namely those with identical row and column values. Else return error sparse matrix multiply A, B. If number of columns in A equals number of rows in B, return the matrix D produced by multiplying O by B according to the formula T//7 equals 5 13 // where D I J is the /7 th element. Else return error. Structure 2.3 Abstract data type sparse matrix creq max row max cot define max terms 101 * type def struct vin call int row int value term A max terms maximum number of terms plus 1 */ The sparse matrix abstract data type 69. Since max terms is greater than 8, these statements can be used to represent the second sparse matrix from Figure 2.3. Figure 2.4 A shows how this matrix is represented in the array A. Thus, A0 row contains the number of rows, AOJ.cos contents number of columns, and A0 the AZO contains the total number of non-zero entries. Positions 1 through 8 store the triples representing the non-zero entries. The row index is in the field row \, the column index is in the field col \, and the value is in the field value. The triples are ordered by row, and within rows by columns. Row call value FL0, 1 2 3 4 5 6 7 8 6 0 0 0 1 1 2 4 5 A 60351230281522 minus 15113 minus 69128H0 1 2 3 4 5 6 7 8 600122335 B 60411502081159111 minus 6 minus 15 figure 2.4 sparse matrix and its transpose stored as triples 2.4.2 transposing a matrix. Figure 2.4 B shows the transpose of the sample matrix. To transpose a matrix, we must interchange the rows and columns. This means that each element 2z, y in the original matrix becomes element A greater than L / in the transpose matrix. Since we have organized the original matrix by rows, we might think that the following is a good algorithm for transposing a matrix. For each row, I take element 1, j, value, and store it as element j, value of the transpose, j/I, value. Unfortunately, if we process the original matrix by the row indices, we will not know exactly where to place element 7, / value in the transpose matrix until we have processed all the elements that precede it. For instance, in figure 2.4, we have 70 arrays and structures 0, 0, 15, 0, 3, 22, 0, 5, dash 15, which becomes 0, 0, 15, 3, 0, 22, 5, 0, dash 15. If we place these triples consecutively in the transpose matrix, then, as we insert new triples, we must move elements to maintain the correct order. We can avoid this data movement by using the column indices to determine the placement of elements in the transpose matrix. This suggests the following algorithm. 1. I. For all elements in column J, place element J, value element J, I, value bin. The algorithm indicates that we should find all the elements in column 0 and store them in row 0 of the transpose matrix, find all the elements in column 1 and store them in row 1, etc. Since the original matrix ordered the rows, the columns within each row of the transpose matrix will be arranged in ascending order as well. This algorithm is incorporated in Transpose, Program 2.7. The first array, A, is the original array, while the second array, B, holds the transpose. It is not too difficult to see that the function works correctly. The variable, current, holds the position in B that will contain the next transpose term. We generate the terms in B by rows, but since the rows in B correspond to the columns in A, we collect the non-zero terms for row I of B by collecting the non-zero terms from column I of A. Analysis of transpose. Determining the computing time of this algorithm is easy since the nested for loops are the decisive factor. The remaining statements, 2 if statements, and several assignment statements require only constant time. We can see that the outer for loop is iterated A0, cc/times, where A0.co/ holds the number of columns in the original matrix. In addition, one iteration of the inner for loop requires A0j, vazu time, where A-q value holds the number of elements in the original matrix. Therefore, the total BME for the nested for loops is columns elements. Hence, the asymptotic time complexity is Q, columns elements. We now have a matrix transpose algorithm with a computing time of O, columns elements. This time is a little disturbing since we know that if we represented our matrices as two-dimensional arrays of size rows x columns, we could obtain the transpose in O, rows columns, time. The algorithm to accomplish this has the simple form. The sparse matrix abstract data type 71B is set to the transpose of a void transpose, term A, term B, / /A0, row, / equals N, asterisk / equals 1, 0, 0, I. Total number of elements rows in B equals columns in B columns in A equals rows in A / asterisk / non-zero matrix asterisk / in N ij, current, n equals a0, value, b0, row, a0.call, b0.call equals b0, value if n0. Current for I equals a01.call, I++, transposed by the columns in a for, j equals 1, j equals n, /***/ find elements from the current column if a j.call equals I / element is in current column, add it *// to b current, row equals a j.call, b current.call equals a j, row, b current, value equals a j, value, current ++, *// program 2.7, transpose of a sparse matrix 0, j equals 0, ii++. For j equals 0, columns, j++ for I rows, bj, I, a, I, j, becomes rows, when the number of elements is of the order columns rows. The O columns elements, time for our transpose function O columns caret. Perhaps, to conserve space, we have traded away too much time. Actually, we can create a much better algorithm by using a little more storage. In fact, we can transpose a matrix represented as a sequence of triples in O columns plus elements, time. This algorithm, fast transpose, program 2.8, proceeds by first determining the number of elements in each column of the original matrix. This gives us the number of elements in each row of the transpose matrix. From this information, we can determine the starting position of each row in the transpose matrix. We now can move the elements in the original matrix one by one into their correct position in the transpose matrix. We assume that max_COL is defined as follows and that the number of columns in the original matrix never exceed it. Arrays and structures 1 */ to find max_COL 50 * maximum number of columns plus void fast transpose. Term A. Term B. The transpose of A is placed in B int row terms, max_COL, starting POS, max_COL. Int ij, number calls equals a0.call, number terms equals a0, value, b0, row equals number calls, b0, value if, number terms 0, a slash for I0, I row terms, I4, I equals number terms, 1, row terms, ai.call for dash plus. Starting POS Q for I starting POS, I equals starting POS, I1 plus row terms, I1 number terms, A0, row, B0.call number terms, non-zero matrix number calls, I++, 0, I++, */1, I equals 1, number calls, I++. For I equals 1, equals IN, a J equals starting POS, AI, call. N dash bj row equals ai.call bj value equals ai value bj.call equals ia row. Program 2.8 fast transpose of a sparse matrix. Analysis office transpose. We can verify fast transpose works correctly from the preceding discussion and the observation that the starting point of row I greater than one of the transpose matrix is row terms il plus where row 5 zl is the number of elements in row z, 1 and starting POS il is the starting point of row z, 1. The first two for loops compute the values for row terms, the third for loop carries out the computation of starting POS, and the last for loop places the triples into the transpose matrix. These four loops determine the computing time of fast transpose. The bodies of the loops are executed number calls, number terms, number calls, 1 and number terms times, respectively. Since the statements within the loops require only constant time, the computing time for the algorithm is O columns plus elements. The time becomes O columns rows when the number of elements is of the order columns rows. This time equals that of the two-dimensional array representation, although fast transpose has a larger constant factor. However, when the number of elements is sufficiently small compared to the maximum of columns or rows, fast transpose is much faster. Thus, in the sparse matrix abstract data type 73. This representation we save both time and space. This was not true of transpose since the number of elements is usually greater than m⁴lx columns, rows, and columns elements is always at least columns rows. In addition, the constant factor for transpose is bigger than that found in the two-dimensional array representation. However, transpose requires less space than fast transpose since the latter function must allocate space for the row terms and starting POS arrays. We can reduce this space to one array if we put the starting positions into the space used by the row terms as we calculate each starting position. If we try the algorithm on the sparse matrix of figure 2.4a, then after the execution of the third for loop, the values of row terms and starting POS are row terms equals starting POS equals 0, 1, 1, 11, 2, 2, 21, 2, 4, 3, 2, 6, 41, 0, 8, 5, 1, 8. The number of entries in row I of the transpose is contained in row terms I \. The starting position for row I of the transpose is held by starting POS I. 2.4.3. Matrix multiplication. A second operation that arises frequently is matrix multiplication, which is defined below. Definition: given A and B where A is mxn and B is nxp, the product matrix D has dimension mxp. Its ij element is zls caret I caret kj k sadface for 0 I less than m and 0 j less than p. The product of two sparse matrices may no longer be sparse, as figure 2.5 shows. N001 FL111 N111 111110000000000111 figure 2.5. Multiplication of two sparse matrices. Arrays and structures. We would like to multiply two sparse matrices represented as an ordered list, figure 2.4. We need to compute the elements of D by rows so that we can store them in their proper place without moving previously computed elements. To do this, we pick a row of A and find all elements in column J of B for J equals 0, 1. Calls B 1. Normally, we would have to scan all of B to find all the elements in column J. However, we can avoid this by first computing the transpose of B. This puts all column elements in consecutive order. Once we have located the elements of row I of A and column J of B, we just do a merge operation similar to that used in the polynomial addition of section 2.2. We explore an alternate approach in the exercises at the end of this section. To obtain the product matrix D, mult, program 2.9, multiplies matrices A and B using the strategy outlined above. We store the matrices A, B, and D in the arrays A, B, and D, respectively. To place a triple in D and to reset sum to 0, mult uses store sum, program 2.10. In addition, mult uses several local variables that we will describe briefly. The variable row is the row of A that we are currently multiplying with the columns in B. The variable row begin is the position in of the first element of the current row, and the variable column is the column of B that we are currently multiplying with a row in A. The variable totaled is the current number of elements in the product matrix D. The variables I and J are used to examine successively elements from a row of A and a column of B. Finally, the variable new B is the sparse matrix that is the transpose of B. Notice that we have introduced an additional term into both A fozas filial, row equals rows A winky face, and new B total plus I, TOW equals calls B winky face. These dummy terms serve as sentinels that enable us to obtain an elegant algorithm. / multiply two sparse matrices void mult, term A, term B, term D, / int I, J, column, total equals BLO, value, totaled int rows totala, A0, value, int row begin, 1, row equals int new B, max terms, 3. If calls A equals B0, row, IA0, row, calls A equals A0 dot call, calls B equals B0 dot call, A1, row, sum equals 0, sprint, stare, incompatible matrices \n, exit 1, 0, a fast transpose b newbie. Set boundary condition A, totala plus L, row equals rows A, newbie, total plus 1, row equals calls B, newbie, total plus 1. Call for I equals 1, I equals totala, column equals newbie 1, row, /**/0, for J equals 1, J equals total plus 1 winky face. The sparse matrix abstract data type 75 multiply row of a by column of B if AI row equals row, a store sum D and totaled row, column, and sum I equals row begin for newbie J, row equals column J plus plus, column equals newbie J row, else if newbie J row equals column, a store sum D, totaled row, column, and sum 1 equals row begin, column equals newbie J row. Else switch, compare, AI.call, newbie J.call, a case -1 / caret go to next term in A/I plus plus, case 0 / sum plus equals break, case 1 * D plus plus, break. Add terms, go to next term in A and AI plus plus, value advance to next term in BK B */ newbie J plus plus, value, / JK / and for J4, AI, row equals row, total plus 1 I plus plus, * row begin equals I. End of for I equals totala D0, row equals rows D0, call calls B, D0, value totaled, or row equals AI. Program 2.9, Sparse Matrix Multiplication. Analysis of mult. We leave the correctness proof of mult as an exercise and consider only its complexity. Besides the space needed for A, / D, and a few simple variables, we also need space to store the transpose matrix newbie. We also must include the additional space required by fast transpose. The exercises explore a strategy for mult that does not explicitly compute new H. We can see that the lines before the first for loop require only O calls B plus total time, which is the time needed to transpose B. The outer for loop is executed totala times. At each iteration either I or J or both increase by 1, or I and column are reset. The maximum total increment in J over the entire loop is total plus 1. If terms row is the total number of terms in the current row of A, then I can increase at most terms row times before I moves to the next row of A. When this happens, we reset / to row begin and
add
76 arrays and structures void store sum, term D, int * totaled, int row, int column, int * sum, / if sum equals 0, then it along with its row and column position is stored as the if sum * totaled plus L entry in D/I. If totaled equals row, D * totaled call, D * totaled, value * sum 0, max terms. Column equals * sum, else print stare. Numbers of terms in product exceeds %D \n, max terms, exit 1. Program 2.10, store sum function plus. The same time, advance column to the next column. Thus, this resetting takes place at most calls B time. And the total maximum increment in I is calls B caret terms row. Therefore, the maximum number of iterations of the outer for loop is calls B caret terms row plus total. The time for the inner loop during the multiplication of the current row is O calls B caret terms row, I total, and the time to advance to the next row is Q terms row. Thus, the time for one iteration of the outer for loop is Q calls B caret terms row, I total. The overall time for this loop is O caret calls B terms row plus total equals O calls caret B total A plus rows A total row. Once again, we can compare this time with the computing time required to multiply matrices using the standard array representation. The classic multiplication algorithm is the sparse matrix abstract data type 770 I 0 j equals 0 for I equals 4 j sum for k 0 k sum plus equals a I j sum I plus plus rows a calls b j plus plus calls a k plus plus b k 3. This algorithm takes O, our 67W5-3 calls A, calls B, time. Since Tadala calls a rows A and Totalb calls a calls B, the time for mult is at most Q rows A, calls B. However, its constant factor is greater than that of the classic algorithm. In the worst case, when Tadala equals calls A rows A or Totalb equals calls A calls B, mult is slower by a constant factor. However, when Tatala and Totalb are sufficiently smaller than their maximum value, that is, A and 3 are sparse, mult outperforms the classic algorithm. The analysis of mult is not trivial. It introduces some new concepts in algorithm analysis, and you should make sure that you understand the analysis. This representation of sparse matrices permits us to perform operations such as addition, transpose, and multiplication efficiently. However, there are other considerations that make this representation undesirable in certain applications. Since the number of terms in a sparse matrix is variable, we would like to represent all our sparse matrices in one array, as we did for polynomials in section 2.2. This would enable us to make efficient utilization of space. However, when this is done, we run into difficulties in allocating space from the array to any individual matrix. These difficulties also occur with a polynomial representation and will become even more obvious when we study a similar representation for multiple stacks and queues in section 3.4. Exercises. Write C functions read matrix, print matrix, and search that read triples into a new sparse matrix. Print out the terms in a sparse matrix and search for a value in a sparse matrix. Analyze the computing time of each of these functions. Rewrite fast transpose so that it uses only one array rather than the two arrays required to hold row terms and starting POS. 3. Develop a correctness proof for the mult function. Analyze the time and space requirements of fast transpose. What can you say about the existence of a faster algorithm?
1, 2, 4.
78 arrays and structures. 5. Use the concept of an array of starting positions found via fast transpose to rewrite mult so that it multiplies sparse matrices A and B without transposing B. What is the computing time of your function? 6. As an alternate sparse matrix representation, we keep only the non-zero terms in a one-dimensional array value in the order described in the text. In addition, we also maintain a two-dimensional array, bits raw, columns, such that bits I, j equals 0 if / 0 and /zv /czll/ equals 1 if / 0. Figure 2.6 illustrates the representation for the sparse matrix of figure 2.4 b. 151 are 100101110 10010000000001000000010000000 22 minus 15 11 3 minus 6 90 128. Figure 2.6. Alternate representation of a sparse matrix A, B, C on a computer with W bits per word. How much storage is needed to represent a sparse matrix? A, with T non-zero terms? Write a C function to add two sparse matrices A and B represented as in figure 2.6 to obtain D, A plus B. How much time does your algorithm take? Discuss the merits of this representation versus the one used in the text. Consider the space and time requirements for such operations as random access, add, multiply, and transpose. Note that we can improve the random access time by keeping another array, RA such that RA / equals number of non-zero terms in rows 0 through Z1. 2.5 Representation of multidimensional arrays. The internal representation of multidimensional arrays requires more complex addressing formulas. If an array is declared A, upper, caret, upper J, upper and happy face, then it is easy to see that the number of elements in the array is RTI/equals 0, where H is the product of the uprays. For instance, if we declare A as a 10, 10, 10, then we require 10, 10, 10 is equal to 1,000 units of storage to hold the array. There are two. Representation of multidimensional arrays 79. Common ways to represent multidimensional arrays: row major order and column major order. We consider only row major order here, leaving column major order for the exercises. As its name implies, row major order stores multidimensional arrays by rows. For instance, we interpret the two-dimensional array A upper Q, upper E as upper caret rows, row O, raw J, RAWYPP happy face Q underscore I, each row containing upper Y elements. If we assume that A is the address of A0, 0, then the address of AZ0 is OC plus I upper X because there are zeros, each of size upper J, preceding the first element in the ZTH row. Notice that we haven't multiplied by the element size. This follows convention in which the size of the elements is automatically accounted for. The address of an arbitrary element, A's fidge, is A plus Z upper J plus J. To represent a three-dimensional array, A upper Q backslash upper E, upper 2. We interpret the array as upper 0 two-dimensional arrays of dimension upper 1y. Upper 2. To locate UZ, 7j, caret, we first obtain A-1, I upper 1 upper, as the address of AZ, 0, 0. Because there are I two-dimensional arrays of size upper 1 upper 2 preceding this element, combining this formula with the formula for addressing a two-dimensional array, we obtain A plus I upper 2 plus J, upper 2 plus K as the address of AZ, 7. Generalizing on the preceding discussion, we can obtain the addressing formula for any element A ZU I, Z underscore I in an n-dimensional array declared as A upper Q, upper X, upper nervous face if A is the address for X 0 J 0. 0, then the address of A/O 0 is A plus ZO upper 2. Upper NI, the address of A0 is A plus ZO upper backslash upper 2. Upper caret dash plus ZL upper 2 upper 3. Upper caret dash, repeating in this way the address for A/O/1. Z underscore I is A plus I upper 2 upper caret, I plus I backslash upper 2 upper underscore backslash plus I 2 upper caret, upper underscore I plus I underscore 2 upper caret, I plus white equals AI, I judge where J sad face, and L and upper 0 J less than N dash backslash K equals I plus backslash N dash backslash equals 1. 80 arrays and structures. Notice that AJ may be computed from 0 J dash using only one multiplication as upper 0, upper phi dash backslash, and use them to compute the constants using n, 2. Multiplications. The address of AZQ, CNN be computed using the formula, requiring n one more multiplications and n additions and n subtractions. Caret 7 plus 1, thus, a compiler will initially take the declared bounds exercises 1, 2, 3. Assume that we have a one-dimensional array, A max SLZ backslash. Normally, the subscripts for this array vary from 0 to max size 1. However, by using pointer arithmetic, we can create arrays with arbitrary bounds. Indicate how to create an array and obtain subscripts for an array that has bounds between -10 to 10. That is, we view the subscripts as having the values -10, -9, -8, 8, 9, 10. Extend the results from exercise 1 to create a two-dimensional array where row and column subscripts each range from -10 to 10. Obtain an addressing formula for the element A/OLCG in NN array declared as A uppers. I assume a column major representation of the array with one word per element, and the address of A0, 0, 0. In column major order, the entries are stored by columns first. For example, the array A3, 3 would be stored as A0, 0, AL, 0, A2, 0, A0L, A1, 1, A2, 1, A0, 2, AL, 2, A2, 2. 2.6 The String Abstract Data Type 2.6.1 Introduction. Thus far, we have considered only ADTs whose component elements were numeric. For example, we created a sparse matrix ADT and represented it as an array of triples row, col, value. In this section, we turn our attention to a data type, the string, whose component elements are characters. As an ADT, we define a string to have the form 5 equals 50, where C are characters taken from the character set of the programming language. If n equals 0, then S is an empty or null string. There are several useful operations we could specify for strings. Some of these operations are similar to those required for other ADTs. Creating a new empty string, reading a string or printing it out, appending two strings together, called concatenation, or copying a string. However, there are other operations that are unique to our new ADT, including comparing strings, inserting a substring into a string, removing a substring from a string, or finding a pattern in a string. We have listed the essential operations in Structure 2.4, which contains our specification of the string ADT. Actually, there are many more operations on strings, as we shall see when we look at part of C's string library in Figure 2.7. The string abstract data type 81 structure string is objects, a finite set of 0 or more characters. Functions for all 5, tg string, I, j, m, e non-negative integers string null, m. Integer compare, 5, z, boolean is null, 5. Integer length, 5. String concat, 5. T, string subster, s, z, 7. Return a string whose maximum length is m characters, but is initially set to null. We write null as if 5 equals t return 0 else if y precedes t return minus 1 else return plus 1 11 11. If compare 5 null, return false else return true. If compare 5 null, return the number of characters in 5 else return 0. If compare z null, return a string whose elements are those of 5 followed by those of t else return 5. If a 7 greater than 0 and z plus 7, I, a length 5, return the string containing the characters of 5 at position z, I plus 1. Z plus 7, I, else return null. Structure 2.4, Abstract Data Type String. In C, we represent strings as character arrays terminated with the null character \0. For instance, suppose we had the strings dog, house. Hashtag define max size 100 / maximum size of string char s, max size, char t, max size, */ Figure 2.8 shows how these strings would be represented internally in memory. Notice that we have included array bounds for the two strings. Technically, we could have declared the arrays with the statements char s, dog. 82 arrays and structures function char *strucat, char *dest, char *src, char *stumcat, char *dest, char *src, in, char *strcmp, char *strl, char *str2, char *strncmp, char *strl, char *str2, in n. Char à la puissance struct char à la puissance dest, char à la puissance src, char à la puissance string pi, char à la puissance dest, char à la puissance src, intn, site char astérisque 5, char à la puissance strchr, char astérisque 5, intc, char à la puissance strchr, char astérisque 5, intc. Char *strdoc, char *5, char *delimiters, char *str, char *5, char *pat, size tsdr sbn, char *s, char *span set, size T str CSBN, char asterisk S, char asterisk span set, char caret strippercatcher asterisk 5, char caret span set. Description concatenate dest and strings. Return result in dest concatenate dest and characters from 5RC. Return result in dest compare two strings. Return 0 if strl str2 backslash. If 5zr7 equals str2 dash. 0 if 5rr7 str2 compare first and characters return 0 if 5zr7 str2. 0 if 5zr7 equals str2 foot. 1 if strl str2. Copy src into dest. Return copy n characters from src string into dest. Return jc caret z. Return the length of a 5 return pointer to the first occurrence of C and S. Return null if not present return pointer to last occurrence of C and 5. Return null if not present return a token from S. Token is surrounded by delimiters return pointer to start of pad in 5. Scan 5 for characters in span set. Return length of span scan 5 for characters not in span set. Return length of span. Scan 5 for characters in span set. Return pointer to first occurrence of a character from span set figure 2.7. See string functions. The string abstract data type 83 SEO cell says SE31 well TLJ TZL tray T 4 T51A09 backslash 0 OU EH backslash 0 S figure 2.8 string representation in C char T house. Using these declarations, the C compiler would have allocated just enough space to hold each word, including the null character. Now, suppose we want to concatenate these strings together to produce the new string, doghouse. To do this, we use the C function strcat, C figure 2.7. Two strings are joined together by strcat S, T, which stores the result in 5. Although 5 has increased in length by 5, we have no additional space in 5 to store the extra 5 characters. Our compiler handled this problem inelegantly. It simply overwrote the memory to fit in the extra 5 characters. Since we declared to immediately after 5, this meant that part of the word, house, disappeared. We have already seen that C provides a built-in function to perform concatenation. In addition to this function, C provides several other string functions which we access through the statement tinclude stringed h. Figure 2.7 contains a brief summary of these functions. We have excluded string conversion functions such as atwa. For each function, we have provided a generic function declaration and a brief description. Rather than discussing each function separately, we next look at an example that uses several of them. For further information on string functions, including examples, look at the books by Kiminghan and Ritchie or Harbison and Steele cited in the references and selected readings section. Example 2.2. String insertion. Assume that we have two strings, say string I and string 2, and that we want to insert string 2 into string 1 starting at the /th position of string 1. We begin with the declarations. Stringed h greater than s equals stringle, asterisk t equals string 2, tinclude hashtag define max size 100 / asterisk size of largest string asterisk / char stringle, max size, char strings, max size. In addition to creating the two strings, we also have created a pointer for each string. Now suppose that the first string contains allmobile and the second contains udo, figure 2.9. We want to insert udo, starting at position 1 of the first string, thereby producing the word automobile. We can accomplish this using only 3 function calls, as figure 2.9 illustrates. Thus, in figure 2.9a, we assume that we have an empty string that is pointed to by temp. We use strncpy to copy the first / characters from 5 into temp. 84 Arrays and structures. Since I equals 1, this produces the string A. In figure 2.9b, we concatenate temp and t to produce the string auto. Finally, we append the remainder of 5 to temp. Since stringcat copied the first I characters, the remainder of the string is at address 5 +/. The final result is shown in figure 2.9c. \0 temp backslash 0 initially backslash 0. A. After strncpy temp si backslash q. B. After strcat temp t. C. After strcat temp is figure 2.9. String insertion example backslash 0. Program 2.11 inserts one string into another. This particular function is not normally found in string.h. Since either of the strings could be empty, we also include statements that check for these conditions. It is worth pointing out that the call strinins s t0 is equivalent to strcat t5. Program 2.11 is presented as an example of manipulating strings. It should never be used in practice as it is wasteful in its use of time and space. Try to revise it so the string temp is not required. 2.6.2 Pattern Matching 5 TAUAAM OBI1 ETUTTOOM 0 BI1E. Now, let us develop an algorithm for a more sophisticated application of strings. Assume that we have two strings, string and pat, where pat is a pattern to be searched for in string. The easiest way to determine if pat is in string is to use the built-in function str. If we have the following declarations. The string abstract data type 85 void strinins char / insert string t *s char *t in I into string s at position I char string max size temp equals string 0 and I stulens * if I print str position is out of bounds \n exit 1 if stulen s strcpy s t else if stulen t strncpy temp s I strcat temp t strcat temp s plus I strcpy s temp. Program 2.11 String insertion function char pat max size string max size *t. Then we use the following statements to determine if pat is in string. If t equals str string pat. Printf. The string from str is else printf. See the pattern was not found with str \n %s\nt. The call t equals str string pat returns a null pointer if pat is not in string. If pat is in string, t holds a pointer to the start of pat in string. The entire string beginning at position t is printed out. Although str seems ideally suited to pattern matching, there are two reasons why we may want to develop our own pattern matching function. 1. 2. The function str is new to ANSI C. Therefore, it may not be available with the compiler we are using. There are several different methods for implementing a pattern matching function. The easiest but least efficient method sequentially examines each character of the string until it finds the pattern or it reaches the end of the string. We explore this approach in the exercises. If pat is not in string, this method has a computing. 86 Arrays and structures time of O and M, where N is the length of pat and W is the length of string. We can do much better than this if we create our own pattern matching function. We can improve on an exhaustive pattern matching technique by quitting when stulen pat is greater than the number of remaining characters in the string. Checking the first and last characters of pat and string before we check the remaining characters is a second improvement. These changes are incorporated in find, program 2.12. Asterisk string, char asterisk pat. Match the last character of pattern first and slash it in find, char slash then match from the beginning in I, j, start equals 0, int last equals stulen, pat, dash 1, int n match equals last, stulen string dash 1. For I 0, n match equals lasts, n match plus plus, start plus plus. If string n match equals pat last, for j equals 0, I equals start, j will last and string I equals pat, j I plus plus ji. If j equals last, return start, /**. Successful *// return -1. A program 2.12. Pattern matching by checking end indices first. Example 2.3, simulation of undefined star. Suppose pat equals ob and string equals ababababa. Figure 2.10 shows how undefined compares the characters from pat with those of string. The end of the string and pat arrays are held by lasts and lasp, respectively. First, undefined compare string, end match, and pat, lasp. If they match, undefined uses I and 7 to move through the two strings until a mismatch occurs, or until all of pat has been matched. The variable start is used to reset I if a mismatch occurs. Analysis of undefined dash. If we apply undefined to string equals AA, and pat equals ob, then the computing time for these strings is linear in the length of the string O, M, which is certainly far better than the sequential method. Although the improvements we made over the sequential method speed up processing on the average, the worst case computing time is still O, M,
N.
The string abstract data type 87AT BAT BAAAAA and match B, T, BBBBA, BT, ATY, BA and match AT, start BA, AB last, A, pattern A, AB, A, AT lasts, B, no match, BA, AB, AA, C, no match. BT, AA, BA and match, D, no match, AT, last B, start B, AT, A, BA, BB, figure 2.10. Simulation of NFT ND match, E, no match AT, lasts A, ATB, T start N match, F, no match B, AT start match ABA. Our lasts BT, A end matcher lasts. 88 arrays and structures. Ideally, we would like an algorithm that works in O, strlen, string, plus strlen, pat, time. This is optimal for this problem, as in the worst case, it is necessary to look at all characters in the pattern and string at least once. We want to search the string for the pattern without moving backwards in the string. That is, if a mismatch occurs, we want to use our knowledge of the characters in the pattern and the position in the pattern where the mismatch occurred to determine where we should continue the search. Nuth, Morris, and Pratt have developed a pattern matching algorithm that works in this way and has linear complexity. Using their example, suppose pat equals abcapicap. Let 5 equals 5052, a 5 to the power of -1 be the string, and assume that we are currently determining whether or not there is a match beginning at 5/. If S happy face, then, clearly, we may proceed by comparing and A. Similarly, if 5/ equals A and 5J plus B, then we may proceed by comparing and A. If 5-5 plus I equals UB and C plus 2, then we have a situation. BB? C9 and 9B5 equals pat equals A. Z, CACA. The implies that we do not know what the character in 5 is. The first in 5 represents 5 dash plus 2 and 5J plus 2C. At this point, we know that we may continue the search for a match by comparing the first character in pat with 5 dash plus 2. There is no need to compare this character of pat with 5 plus I, as we already know. That 5 plus I is the same as the second character of pat, B, and so 5 plus IA. Let us try this again, assuming a match of the first 4 characters in pat followed by non-match, i.e. 5 plus 4B. We now have the situation. BBCCA 9B7C5 equals pat, A, H, ACA. We observe that the search for a match can proceed by comparing 5 plus 4 and the second character in pat, B. This is the first place a partial match can occur by sliding the pattern pat towards the right. Thus, by knowing the characters in the pat term and the position in the pattern where a mismatch occurs with a character in 5, we can determine where in the pattern to continue the search for a match without moving backwards in 5. To formalize this, we define a failure function for a pattern. Definition: if P equals pop J P underscore is a pattern, then its failure function, F, is defined as / equals largest I less than J such that POPI, pi, PJI plus 2, pj if such and z0 exists minus 1 otherwise. The string abstract data type 89 for the example pattern, pat, abcapicab, we have 0tz3 is 0, 4b1j pat, f minus, 11b minus, 11c minus, 11c minus, 15c1 6tz3, 8 a 0 9b1. From the definition of the failure function, we arrive at the following rule for pattern matching. If a partial match is found such that c⁻j, pj dash backslash cpj, then matching may be resumed by comparing s⁻, and if j0, if j equals, then we may continue by comparing as/p. This pattern matching rule translates into function match, program 2.13. The following declarations are assumed. Includes diode, h, hashtag includes string h, hashtag define max underscore string underscore size 100, hashtag define max underscore pattern underscore si 2e 100th match, void fail, int failure, max underscore pattern underscore size, char string, max underscore string underscore size, t char pat, max underscore pattern underscore size. Int match, char /* nuff, Morris, asterisk string, char asterisk pat, prat string matching algorithm 0, j equals 0, int int lens equals strlen string, int length equals strlen pat. While io lens and j length, if stringly equals pat j, I++, else if j equals 0, I++, else j equals failure, j, 1 plus 1, j++, asterisk / or returned, j equals length, I length, minus 1. Program 2.13, Nuth, Morris, Pratt pattern matching algorithm. 90 arrays and structures. Note that we do not keep a pointer to the start of the pattern in the string. Instead, we use the statement return j equals length, I length, minus 1. This statement checks to see whether or not we found the pattern. If we didn't find the pattern index j is not equal to the length of the pattern, and we return minus 1. If we found the pattern, then the starting position is / the length of the pattern. Analysis of match. The while loop is iterated until the end of either the string or the pattern is reached. Since I is never decreased, the lines that increase I cannot be executed more than m equals strlen string times. The resetting of j to failure, jl, plus l decreases the value of j. So, this cannot be done more times than j is increment by the statement j++, as otherwise, j falls off the pattern. Each time the statement j++ is executed, I is also increment. So, j cannot be increment more than m times. Consequently, no statement of program 2.13 is executed more than m times. Hence, the complexity of function match is O, m, equals O, strlen string. From the analysis of match, it follows that if we can compute the failure function in O, strlen, pat, time, then the entire pattern matching process will have a computing time proportional to the sum of the lengths of the string and pattern. Fortunately, there is a fast way to compute the failure function. This is based upon the following restatement of the failure function. If 7 is equal to 0, f less than j equals minus 1f, j 1 plus 1 where m is the least integer k, for which equals pj minus 1 if there is no k satisfying the above. Note that f, j equals f, j and /o, j. This definition yields the function in program 2.14 for computing the failure function of a pattern. Analysis of fail. In each iteration of the while loop, the value of I decreases by the definition of /. The variable I is reset at the beginning of each iteration of the for loop. However, it is either reset to minus 1 initially or when the previous iteration of the for loop goes through the last else clause, or it is reset to a value 1 greater than its terminal value on the previous iteration, i.e., when the statement failure j equals z plus 1 is executed. Since the for loop is iterated only n dash, n is the length of the pattern, times, the value of I has a total increment of at most n1. Hence it cannot be decrement more than nl times. Consequently, the while loop is iterated at most n-backslash times over the whole algorithm, and the computing time on fall is O, n equals O, stolen, pat. The string abstract data type 91 void fail, char pat, / compute the pattern's failure function in n equals stolen pat, failure 0 for j equals L, ji equals failure, j1. While palj equals pat I plus 1, and I failure, I, if pat, j equals pat I plus 1, failure, j I plus 1, else failure, j equals -1, -1, and j */ 0. Program 2.14, computing the failure function. Note that when the failure function is not known in advance, the time to first compute this function and then perform a pattern match is 0 of stolen pat plus stolen string. Exercises 1, 2, 3, 4, 5. Write a function that accepts as input a string and determines the frequency of occurrence of each of the distinct characters in string. Test your function using suitable data. Write a function, sternal, that accepts a string and two integers, start and length. Return a new string that is equivalent to the original string, except that length characters beginning at start have been removed. Write a function, std, that accepts a string and a character. The function returns string with the first occurrence of character removed. Write a function, strpos, that accepts a string and a character. The function returns an integer that represents the position of the first occurrence of character in string. If character is not in string, it returns -1. You may not use the function strpos, which is part of the traditional string h library but not the ANSI C one. Write a function, strcchar1, that does the same thing as strpos1 except that it returns a pointer to character. If character is not in the list, it returns null. You may not use the built-in function strcchar. 92 Arrays and Structures 8. 6. Modify program 2.11 so that it does not use a temporary string temp. Compare the complexity of your new function with that of the old one. 7. Write a function, strsearch, that uses the sequential method for pattern matching. That is, assuming we have a string and a pattern, strsearch examines each character in string until it either finds the pattern or it reaches the end of the string. Show that the computing time for find is O/I/W, where N and M are, respectively, the lengths of the string and the pattern. Find a string and a pattern for which this is true. 9. Compute the failure function for each of the following patterns, A, B, C, 10. Show the equivalence of the two definitions for the failure function. Abeba a ab do ashariya sa. References and selected readings. Several texts discuss array representation in C, including T. Plum, Reliable Data Structures in C, Plum Hall, Cardiff, N.J., 1985, Chapter 3, and R. Jesh, Siliciofis in C, Addison Wesley, Reading, Massachusetts, 1986, Chapter 2. The Jesh text includes a detailed discussion of array bounds, including altering array bounds and pointer addressing. Strings are discussed in B. Chemigan and K. Ritchie, The C Programming Language, ANSI C, 2nd edition, Prentice Hall, Englewood Cliffs, New Jersey, 1988, and S. Harbison and G. Steele, C. A Reference Manual, 3rd edition, Prentice Hall, Englewood Cliffs, N.J., 1991, Chapter 13. A discussion of string pointers can be found in R. Traister, Mastering C Pointers, Academic Press, San Diego, California, 1990. The Nuth, Morris, Pratt pattern matching algorithm is found in Fast Pattern Matching in Strings, Siam Journal on Computing, Volume 6, Number 2, 1977. 2.8 Additional Exercises 2. I, given an array A and produce the array Z, n such that caret 0 equals A, NL, Z, L equals A, and 2, Z, and 2 equals AL, Z. minus 13 equals 70. Use a minimal amount of storage. An MXN matrix is said to have a saddle point if some entry A, ZJLJ, is the smallest value in row I and the largest value in column J. Write a C function that determines location of a saddle point if one exists. What is the computing time of your method? Exercises 3 through 8 explore the representation of various types of matrices that are frequently used in the solution of problems in the natural sciences. Additional exercises 93-3. A triangular matrix is one in which either all the elements above the main diagonal or all the elements below the main diagonal of a square matrix are 0. Figure 2.11 shows a lower and an upper triangular matrix. In a lower triangular matrix, A, with n rows, the maximum number of non-zero terms in row I is I plus 1. Thus, the total number of non-zero terms is NL(Z plus L) equals Ni-2. I equals Q. Since storing a triangular matrix as a two-dimensional array wastes space, we would like to find a way to store only the non-zero terms in the triangular matrix. Find an addressing formula for the elements AJJ so that they can be stored by rows in an array B, and +1/2-1, with A0, 0 being stored in B0.
XX décima XX décima XX décima XX décima X non 00.
XX triple X XX triple X triple X XX 0 triple X non 0 XX XXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXX triangular matrices for
5.
Let A and B be two lower triangular matrices, each with n rows. The total number of elements in the lower triangles is Z, H1. Devise a scheme to represent both triangles in an array. Hint: represent the triangle of A in the D and the transpose B in the upper triangle of D. Write algorithms to determine the values of AI/B/I/0I/J less than n. A tridiagonal matrix is a square matrix in which all elements that are not on the major diagonal and the two diagonals adjacent to it are 0, figure 2.12. The elements in the band formed by these three diagonals are represented by rows in an array B, with A0, F0 being stored in Z0. Obtain an algorithm to determine the value of AZ7, 0, I, J less than n from the array B. 94 arrays and structures XX XXX XXX. X00 XX XXX 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 figure 2.12. Tridiagonal matrix is an nxn matrix in which all the non-zero terms lie in 6. A square band matrix. A band centered around the main diagonal. The band includes the main diagonal and 3 to 1 diagonals below and above the main diagonal, figure 2.13. 4. 3 upper band a diagonals and rows 0 lower band. N columns main diagonal, figure 2.13, square band matrix. Additional exercises 95, A, B, C, pound, I, N, a 7. How many elements are there in the band? What is the relationship between I and J for elements D/Y in the band? Assume that the band of is stored sequentially in an array B by diagonals, starting with the lowermost diagonal. For example, the band matrix D43 of figure 2.13 would have the following representation.
B09, B31, B28, B10, B33, D33, D2, B46, B46, B56, B60, 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 D7, D22, B8, B8, B933, B901.
BL0 4DN bill 9 to the power of 23B 12 802B 13 4 to the power of 13. Obtain an addressing formula for the location of an element D/J in the lower band of location D low equals 2 in the example above. 7. A generalized band matrix D(A to the power of B is an AZXN matrix in which all the non-zero terms lie in a band made up of 3 to 1 diagonals below the main diagonal, and BI bands above the main diagonal, figure 2.14. A, B, N rows and columns main diagonal caret N, A, H figure 2.14. Generalized band matrix. 96 arrays and structures. How many elements are there in the band of? What is the relationship between I and J for the elements Dij in the band of? Obtain a sequential representation of the band D happy face A caret B in the one-dimensional array E. For this representation, write a C function value, N, A, B, I, J, E, that determines the value of element D in the matrix D, caret N dot A. N, A dot B. The band of 7 is represented in the array E, A, B, C.
8.
A complex-valued matrix X is represented by a pair of matrices A, B, where A and B contain real values. Write a function that computes the product of two complex-valued matrices A, B, and D, E, where A *** J E equals A plus IB * D plus IE equals add B plus I AE plus BD. Determine the number of additions and multiplications if the matrices are all nxn. 9-section programming project. There are a number of problems, known collectively as random walk problems, that have been of long-standing interest to the mathematical community. All but the most simple of these are extremely difficult to solve, and for the most part, they remain largely unsolved. One such problem may be stated as: A drunken cockroach is placed on a given square in the middle of a tile floor in a rectangular room of size n xm tiles. The bug wanders, possibly in search of an aspirin, randomly from tile to tile throughout the room. Assuming that he may move from his present tile to any of the 8 tiles surrounding him, unless he is against a wall, with equal probability. How long will it take him to touch every tile on the floor, at least once? Hard as this problem may be to solve by pure probability techniques, it is quite easy to solve using a computer. The technique for doing so is called simulation. This technique is widely used in industry to predict traffic flow, inventory control, and so forth. The problem may be simulated using the following method. An nxm array count is used to represent the number of times our cockroach has reached each tile on the floor. All the cells of this array are initialized to 0. The position of the bug on the floor is represented by the coordinates ibug, jbug. The 8 possible moves of the bug are represented by the tiles located at ibug plus a move, k, jbug plus jmove, kj, where 0, k less than 7, and additional exercises 97 zwov 0 equals -1 equals zm6 v caret 2 equals a move 3 equals zm 9 v caret 4 equals zm 9 v caret 5 equals a move 6 equals -1 zm v caret 7 equals -1011101107m v 0 equals /move l equals jmove 2 equals jmovel 3 equals 7 move 4 equals -1 ym 7 v 5 equals -1 jmovel 6 equals -1 7 m euro v caret 7 equals 0. A random walk to any one of the 8 neighbor squares is simulated by generating a random value for k lying between 0 and 7. Of course, the bug cannot move outside the room, so that coordinates that lead up a wall must be ignored and a new random combination formed. Each time a square is entered, the count for that square is increment, so that a non-zero entry shows the number of times the bug has landed on that square. When every square has been entered at least once, the experiment is complete. Write a program to perform the specified simulation experiment. Your program must A, B, C. Handle all values of n and m, 2 n less than 40, 2 m less than 20. Perform the experiment for 1. N equals 15, m equals 15, starting point 10, 10, and 2, n equals 39, m equals 19, starting point 1, 1. Have an iteration limit, that is, a maximum number of squares that the bug may enter during the experiment. This ensures that your program will terminate. A maximum of 50,000 is appropriate for this exercise. For each experiment, print 1. The total number of legal moves that the cockroach makes and 2. The final count array. This will show the density of the walk, that is, the number of times each tile on the floor was touched during the experiment. This exercise was contributed by Olson. 10. Section Programming Project. Chess provides a setting for many fascinating diversions that are quite independent of the game itself. Many of these are based on the strange L-shaped move of the knight. A classic example is the problem of the Knight's Tour, which has captured the attention of mathematicians and puzzle enthusiasts since the beginning of the 18th century. Briefly stated, the problem requires us to move the knight, beginning from any given square on the chessboard, successively to all 64 squares, touching each square once and only once. Usually we represent a solution by placing the numbers 0, 1, 63 in the squares of the chessboard to indicate the order in which the squares are reached. One of the more ingenious methods for solving the problem of the Knight's Tour was given by J.C. Warnsdorf in 1823. His rule stated that the knight must always move to one of the squares from which there are the fewest exits to squares not already traversed. 98 Arrays and Structures. The goal of this programming project is to implement Warnsdorf's rule. The ensuing discussion will be easier to follow, however, if you try to construct a solution to the problem by hand before reading any further. The crucial decision in solving this problem concerns the data representation. Figure 2.15 shows the chess board represented as a two-dimensional array. 4012356701270136 255431. Figure 2.15. Legal moves for a knight. The 8 possible moves of a knight on square 4, 2 are also shown in this figure. In general, a knight may move to one of the squares I2, 7, 4, 1, /-1, 74, 2, /+1, 7 plus 2, I plus 2, 7 plus 1, Z plus 2, 7, 1, Z plus 1, 7, 2, Z1, 7, 2, Z minus 2, J minus 1. However, notice that if Z, J is located near one of the board's edges, some of these possibilities could move the knight off the board, and, of course, this is not permitted. We can represent easily the 8 possible knight moves by two arrays Kmov 1 and Kmov 2 as. Additional exercises 99 Kmov 1 minus 2 minus 1 1 2 2 1 minus 1 minus 2 Kmov 2 1 2 2 1 I minus 2 minus 2 minus 1. Then a knight at /7 may move to I plus Kmov /7 plus Krnovelk, where Z is some value between 0 and 7, provided that the new square lies on the chessboard. Below is a description of an algorithm for solving the Knight's Tour problem using Warnsdorf's rule. The data representation discussed in the previous section is assumed. A, B, C, D, E, 0. Initialize chessboard for 0 I, J less than 7 set board /7 to 0. Set starting position I read and print /J and then set board Z 7 to 0. Loop for 1 M less than 63, do steps D through G. Form a set of possible next squares. Test each of the 8 squares one knight's move away from /7 and form a list of the possibilities for the next square. Next D, L, next J. Let impose be the number of possibilities. That is, after performing this step we have next D equals plus Kmov 1 K and nextLj equals J plus Kmov K for certain values of K between 0 and 7. Some of the squares, Z plus Kmov 1 J plus /Cznov 2 / may be impossible because they lie off the chessboard or because they have been occupied previously by the knight. That is, they contain a non-zero number. In every case, we will have 0 impose 8. Test special cases. If impose equals 0, the knight's tour has come to a premature end. Report failure and go to step H. If in pose equals 1, there is only one next move. Set min to 1 and go to step G. Find next square with minimum number of exits for 1 I in pose. Set exits Z to the number of exits from square. Next D / next gel. That is, for each of the values of Z, examine each of the next squares. Next D Z plus move 1 caret. Next E Z plus 2 A to see if it is an exit from. Let next D I, next I, and count the number of such exits in exits I. Recall that a square is an exit if it lies on the chessboard and has not been occupied previously by the knight. Finally, set min to the location of the minimum value of exits. If there is more than one occurrence of the minimum value, min denote the first such occurrence. Although this does not guarantee a solution, the chances of completing the tour are very good. 100 arrays and structures, G. Move knight set I equals next D M, J equals next min and / equals M. Thus, / J denotes the new position of the knight and board / records the move in proper sequence. H. Print out the board showing the solution to the knight's tour and then terminate the algorithm. Write a C program that corresponds to the algorithm. This exercise was contributed by Legenhausen and Redman.